All right, welcome to today's Corundum developer meeting. Thanks to everyone for tuning in. So for today, we just have a few status updates primarily. So I'll go ahead and get into that. All right, so in terms of recent updates and stuff I'm going to be working on in the near future, I've been doing a lot of work on PCI Express and interrupt handling over the past couple of weeks. So I've done a bunch of work on the PCI Express simulation models to, improve those both in terms of supporting MSIX and in terms of making them a little bit easier to use. And then I've also implemented MSIX on the hardware side and ported Corundum over to use the new MSIX components. So I think what I'm going to do here is, Corundum is only going to use MSIX. I'm going to drop MSI completely, although we can potentially revisit that if there's some device that doesn't support MSIX, perhaps. Easier to support just one method for interrupt handling. The next thing that I'm going to be working on is getting the segmented PCI Express interface operational. This is connecting to the IP cores on the various devices. So this will hopefully improve the performance, not only by getting a slightly higher throughput, but also by avoiding some bugs on Xilinx devices, and then also by supporting PCIe Gen 3 by 16 and wider interfaces on things like the Intel FPGAs that require the segment interface under those circumstances. And then after that, I'm going to take a crack at getting variable length descriptors operational. And then the other to-do items that have carried over: management software, link rate switching, and the clock info register block that I need to get hammered out. All right, so moving on to some more details here. So the PCIe IP core or PCIe model updates that I've implemented, the main thing are I started working on implementing MSIX, and then I realized that the way I was doing the enumeration, I was kind of doing everything at the same time, and until you get all of the bars enumerated properly and get all of the PCIe switch settings configured, you can't access any of the bar space on any of the devices. So the setup that I had worked for setting up MSI and doing all the device configuration at the PCI Express config space level, but it doesn't work for MSIX because for that I have to actually write to the bars. So what you have to do is do the entire enumeration first, get everything all set up in terms of the PCI Express ID routing and the bar registers and memory space routing and all of that stuff. And then you can go back and configure MSIX. So I figured, okay, maybe it's time to kind of do an overhaul of the host software abstraction effectively in the model and kind of make it look a little bit more like how Linux works. So that's what I did. I pulled all of the enumeration code out of the root complex model, and I separated the bus and device objects. I got rid of this tree item object that I had before and basically just made that PCI Express device. And then I also added a bus object, so the enumeration scheme and whatnot now follows more what the Linux kernel does. And now instead of doing a bunch of stuff just implied through the top level call to enumerate on the root complex, I have separate calls for enable device set master, request IRQ vectors, things like that. Similar to what you have in the Linux kernel that you call on the individual PCI device after you've fetched it from the software model. So this, I'm not going to say it simplifies things necessarily, but it makes it a little bit closer to how the Linux kernel works. And then once I got all that working, then I went and implemented MSIX, and that works in the model, so we can actually test that when you're putting together code on the HDL side. All right, and then in terms of MSIX for Corundum, the plan is basically just to switch straight over to MSIX and to not support MSI. Potentially we can revisit that and add MSI support back later, but I think it's going to be simpler if we just support one method, and MSIX is going to be more flexible while not requiring very much additional, while not requiring very many additional logic resources, just a couple of block grams pretty much. And things like SRIOV apparently require MSIX, and some systems limit to MSI to one vector. So supporting MSIX, I think, is going to be the most flexible, long term. And the status right now is working on both Xilinx and Intel devices. I have yet to go and test all of the Corundum target devices to make sure that I haven't broken anything when adding support for MSIX. But I'm probably going to wait on doing that until I have a couple of other things implemented, just because it takes some time to do that. So if I can get some of the other changes done to the PCI Express interfaces, then I can just test everything and get it all pushed up to the main repository. I've gone ahead and pushed it to my development fork, but it has not yet gone to the main core repository yet. So hopefully that will be coming within the next few weeks. All right. The next thing I'm starting to work on now is the segmented PCI Express interface. And the idea with this is that when you're exchanging packets with the hard IP on the FPGA for PCI Express, in some cases, you'll want to transfer potentially parts of multiple TLPs in the same clock cycle. So either multiple TLPs or like the end of one and the start of the next. And the idea here is that this will improve the throughput into the PCI Express IP core, because you might have, if you're transferring small packets over a very wide interface, or you're transferring packets that are not aligned with the interface width, then you're going to be wasting effectively bandwidth. So, and in some cases, this is required. So for like the Xilinx devices, you can turn it off, and you could run with a single segment. For the Intel devices, you can't. So you have to deal with this one way or another if you're using the wider interfaces. So for like PCIe Gen 3x8 on the Stratix 10 devices, that runs with one segment, so you don't need this. But if you do Gen 3x16, now that's two segments of 256 bits. So yeah, you need to do something to, stripe packets across those segments on transmit and de-stripe it on receive, unless you want to make the DMA engine and everything else also segmented. So I'm not going to make the DMA engine segmented right now, but I'm going to look at, implementing some sort of an adaptation basically between the IP core and the DMA engine, so that things will work and we'll get a little bit more throughput. Right, and I'm also suspecting that implementing this interface will work around a bug that I stumbled across in the Xilinx PCIe IP core that's resulting in garbage TLPs on the RC interface from the host when more than 64 tags are used. So if we get the segment interface working and we alleviate this bug, then hopefully we'll be able to use more tags, which will also result in more throughput on the Xilinx devices, at least in terms of PCI Express reads. Writes will not be affected by this. Well, they won't be affected by the number of tags, but we could get a throughput improvement with the segmentation. All right, so the status on this is it's in progress. I am starting to get my head wrapped around what needs to be done. So this is kind of the plan for right now. So I've gone ahead and I've updated the Xilinx PCIe IP core model to support TLP straddling. So that was another update that I pushed to the PCI Express model. And the current plan is to implement kind of a generic segmented FIFO, segmented MUX demux module, and then improve the device-specific interface adapters to work with the segmented interface. So the FIFO is probably going to be the most complicated part of this, and the idea is it'll support N segments on one end and M segments on the other. So you might have one segment on the input and 2 or 4 segments on the output, or vice versa. So the FIFO internally will stripe the data across all of the internal segments, removing any segments that don't contain any data. And then the output will be packed with the proper alignment. So, if you only have one segment, then all the TLPs will have to start in the first in the first segment. Well, in the first lane rather. If you have multiple segments, then the TLPs will be, they'll come out back to back without any gaps. So yeah, this is going to require a little bit of logic on both the input side and the output side, and then multiple internal FIFOs effectively to make it work. So, I mean, I mentioned crossbar a couple times in here, but it's like, for like if you have the RC interface on the Xilinx devices, that's just 4 segments. So you got to remap 4 segments from the IP core into 4, internal FIFOs, which is, I don't think that'll be too terrible, but we'll see. Right, so that's segmented FIFO, and then we'll have a multiplexer module that can take TLPs from multiple sources, and it has to do this kind of on a segment by segment basis to get full throughput. So that one could also be a little bit complicated. We'll see. Then the demux has to extract TLPs across multiple segments and presumably put those in the FIFO. So I think the demux is not going to be too bad, but the FIFO will have to be able to take packets from lanes other than lane 0, basically, and pack them appropriately, which complicates the FIFO a little bit, but I don't think by all that much. And then the idea would be to implement adapters that can take the raw interface from the PCI Express IP core and convert it to the internal interface that I'm using in the PCI Express setup. So this is, peeling off the header and transferring the header as sideband data, and then repacking the data so it's all nicely aligned. So yeah, I think this is all doable, but it's going to take some time to get everything working. Let's see. And then after I get that operational, then I'm going to take a crack at variable length descriptor support. So more details on that. More details on that later. Let's see. So we will go ahead and take a look at performance with MSIX, just since I now have a few numbers here for that. So this is running on my development machine, this guy right over here that I put together recently. It's a Dell 7920 workstation machine with dual Intel Xeon 6130 CPUs. And I haven't used this one too much before for benchmarking because this one limits MSI to 1 channel. So now that I have MSIX working, we can go ahead and run on there and see what the performance looks like. And this is a slightly different machine from the ones that were used in the FCCM paper. So I think the numbers should be similar, but I mean, it's like ideally I think they should be similar, but we are seeing a few differences in performance versus what was done for FCCM. So that's potentially some area for improvement. A lot of stuff has changed. I'm not sure exactly what where the performance limitations are coming from. I don't think I'm going to spend too much time optimizing stuff until I have variable length descriptors operational, but at least this gives a bit of a baseline for kind of the current version of Corundum. I'm going to be trying to do more benchmarking as improvements are made, just to make sure that that things are moving in the right direction. There may be some other tunables I need to look at as well. I think I also played around with some of the operation table sizes a little bit as well when I was working on the FCCM stuff. So anyway, this test was done with the Alveo U200, 8192 transmit queues, 256 RX queues, 64 event queues, and 64 MSIX channels. This was with MTU 9000. So we can get on the RX side, we can hit pretty close to line rate. I'm thinking we're starting to run into the limitations of the segmented interface to the PCI Express IP core with that. So hopefully this will improve a little bit once I have the segmented interface implemented and operational. On the TX side, for some reason, the performance is quite a bit lower. I'm not sure exactly what's going on with that. It still gets up to 100 gig, but it looks like each process is running at about half the throughput. So I might need to do some more work to try and figure out if this is a software issue or if the each individual transmit queue is just running a lot lower. This is, compared to the FCCM paper, I think these curves were more or less on top of each other, or the TX might have even been faster than the RX. Not sure. Need to follow up on that. But for the simultaneous, we're hitting around 60 or 70 gigabits per second when we're running both TX and RX at the same time. I'm not sure if I mentioned this before, but these two curves are kind of converging on more or less the same, or on a similar level. So it seems like there's a shared resource that's being shared between the TX and the RX traffic. And I'm assuming that this is probably the descriptor fetches. So because both the TX and the RX have to fetch descriptors from the transmit and RX queues, if we're limited in terms of the number of descriptors per second that we can fetch, then that's going to limit the throughput and kind of the aggregate throughput if you add the TX and RX together. So hopefully, once I get variable length descriptor support working, this situation will be improved. But it's also possible that this is a host limitation here. Not quite sure, but definitely some room for improvement. So this is with MTU 9K. If we run it for MTU 1500, the results are not quite as good. Yeah, so in this case, the TX, it's slowly working up, but with 8 processes, it's only hitting about 80 gigabits per second. I didn't test with higher than 8, at least for this particular round. I thought we were able to get higher than this on the FCCM paper, but I'll take another look at that. And then the RX performance that's capping out around 60. I think I'll have to take a look at what the FCCM paper was doing for this, but hopefully this can be improved with some of the with improvements in the driver, particularly around memory management and whatnot. So we'll have to see. So this is going through the Linux kernel networking stack and whatnot. I'm not sure if you're doing, some bypassing stuff, if you might be able to get better performance than this. And then if you run simultaneous, again, we're seeing this similar behavior where these two are kind of converging at the same throughput. So I'm thinking we're starting to run into some limitations of the descriptor fetch subsystem. So hopefully once I have the variable length descriptor support working, we'll be able to read these descriptors in larger blocks instead of one at a time, and cache them for a while, which should help improve the packet rate and the overall throughput. Right, so food for thought. These are somewhat initial measurements because I haven't been doing benchmarking in quite a while. So hopefully we'll be able to take these and improve upon them. All right, let's see. So I guess I'll go ahead and put up my to-do list for a stable release, variable length descriptor support, and that's going to be coming up hopefully within the next few weeks. We'll be able to get that operational. That'll be another thing checked off. Checksum offloading. I put some time into putting together a more generic IP parsing module, but I got to circle back around that and see if I can get that operational. And then the softcore, yeah, once I get variable length descriptor support, then I'll probably take a crack at these other couple of things. But that's going to be slightly longer term. All right, so that brings me to the end of the status updates for this week. If you have any questions or comments or concerns, let me know. Anybody have any questions on any of this?
I have a question, but it may not be related to today's topics.
Sure.
Slightly. Have you ever tried testing how much TX and RX affect each other on PCI set? I mean, when you are receiving packets from RX at maximum line rate, and when you want to send packets to network at maximum line rate, then FPGA sends read requests from the same lanes, right? Of course, in IP, it's a different interface, but they come together via at file layer, right? So do you think they affect each other, and do you think effect is negligible? Also, event queues are also sending some requests, and how much they are affecting overall throughput?
Well, there's definitely an effect. And I think this is maybe showing up a little bit in these graphs here, because you definitely see significantly reduced performance if you're running the transmit and the receive paths at the same time. But what's not clear is how much of that is coming from, you know, the host software in terms of what the CPUs are doing to refill the receive queues and handle receive packets and whatnot, and, you know, free the transmit queues and recycle those buffers and whatnot, versus how much of this is on the hardware side. So that's actually one thing I need to do a little bit more poking around at is, you know, in this regime, if you look at like the depth of the receive queues and the depth of the transmit completion queues, you can get an idea of, you know, who's running ahead of who, right? So in this case, if your transmit queues are full and your receive queues are full, then that means that the hardware is not keeping up with the software. But if the transmit and receive queues are empty, then that means that the software is not keeping up with the hardware. And if the hardware is being slow, then that could indicate a problem on the PCI Express interface side, right? Because yeah, all of that traffic does have to share the same link. But to some extent, the read traffic and the write traffic are handled differently, because there are flow control credits that apply differently to the read requests and versus the write requests, because the read requests are non-posted, whereas the write requests are posted. So in some sense, you can basically send as many write requests as you want, versus for read request, well, I guess that's another factor as well, is that for read requests, you have tags. For write requests, you don't. So you're limited in terms of how many read requests you can use at any one time, because you only have so many tags. For write requests, you can send as many as you want until you get pushback from the host. And one thing that I have set up right now is that I am looking at the amount of available flow control credits. So I don't have head of line blocking between the read requests and write requests. So like if I issue a bunch of writes and the host is like, you can't send anymore, I can still send read requests. And the way that path is set up, you know, that should work as expected, and it shouldn't get blocked up internally. But yeah, potentially, you know, you are sharing the same link, so there is going to be a throughput, you know, overhead there, even if you're not seeing, even if you have enough flow control credits, even if you have enough tags, yeah, you are sharing the same link. So I ran some back of the envelope calculations a while ago, and if you want to get, you know, 100 gigabit per second line rate with, you know, an Ethernet NIC, 1500 byte frames is about the smallest frame that you can actually send or receive. If you try to go smaller than that, then you have to move so many descriptors and so many send so much other traffic over the link that you're not going to be able to get to 100 gig line rate, which is kind of interesting. The numbers work out that way. It's like exactly 1500 bytes. If you go to 1400 bytes, it doesn't work. But so I think I also made some somewhat pessimistic assumptions where, you know, I'm performing individual reads for every single descriptor. If you read them in batches, then there's a little bit less overhead, because, you know, there's actually quite a few bytes on each read request and on each completion that are, you know, effectively wasted in terms of the overall throughput there. So if you can read them in descriptors and write completions in blocks instead of one at a time, then that gives you a little bit more margin. But yeah, this is definitely a concern. And I mean, it's even a concern if you're using something like a Mellanox NIC, right? You know, you're just not going to be able to do line rate at 64 byte packets at 100 gig over PCI Express. I don't care what your NIC is. There's not enough throughput there for that.
Right, and the other thing is, just even if you did get it inside, your CPU wouldn't be able to do any reasonable, decent work with those packets anyway.
Right.
So
yeah. I mean, that's to some extent why I have not concerned myself too much with, trying to achieve some super high packet rate, because there's only so much you can do from the CPU perspective. Although I guess from the flip side is that I've mainly been using the Linux kernel networking stack. So that's much slower than using something like DPDK, right? I know DPDK can hit a, more orders of magnitude more packets per second than the Linux kernel stack.
Right. So on the graph here, the TXS and RXS are like simultaneous.
Happening? TX and RX. So basically it's running the first two experiments at exactly the same time. So, and all the scripts for this are now in the repository. So if you want to run this exact same test, you can. And basically the way it works is it starts up varying numbers of iPerf processes. And iPerf actually supports like 3 different modes of operation. It can support just a TX test, it can do an RX test, and iPerf can actually do a bidirectional test as well. But there's something wrong with how it does a bidirectional test. I don't know what it is, but it does not work properly. And I spent way too much time banging my head against the wall thinking there was something wrong with Corundum, when it turns out it was iPerf being broken. So basically the way the script works is it does 3 different tests that it cycles through. The first one is it runs, X number of iPerf senders, and then it does X number of iPerf receivers. And then the third one is it runs X senders and X receivers at the same time. And then that produces, these 4 curves. So you get 1 curve from the first test, 1 curve from the second test, and 2 curves from the third test. So effectively, the green curve and the red curve are running the first 2 curves, but at exactly the same time. And the numbers that are collected here, the data is pulled from the NIC counters. It's not what iPerf reports. So the way the scripts are set up is it runs iPerf for like 12 seconds. It waits a second after starting iPerf, dumps the counters, and then dumps the counters every second for 10 seconds, basically. And then takes first point, last point, subtracts those, and that's the amount of data that was sent or received or whatever. I also collect information on like packet drops and a couple of other things. So you have some idea what's going on. And iPerf also reports the number of retransmitted packets. So I don't have, I didn't plot that, but it is collected. And we can potentially add more stuff to that at some point too.
Yeah, another question on the graph is the U200 using the same alveoli on both sides, or is it 2 different alveoli parts?
Yeah, I didn't mention that. Yeah, so the link partner in this case was a ConnectX NIC. So I think these are taken with a ConnectX 4, but I also have a ConnectX 5. Okay. And the other thing I guess I should mention is that even though these were both in the same machine, both the sender and the receiver were in the same machine, they were running on different CPUs, and everything was locked to a NUMA node with NUMA control. So ostensibly, that's getting similar performance to running these on 2 different machines, but that's probably something I need to try at some point is actually running with the ConnectX NIC in a different computer and see if that makes much difference. I don't think it will, because each NIC is hooked up directly to one of the CPU sockets. So unless we're getting one CPU using RAM from the other socket, I don't think we have a problem there. But that's actually one thing I didn't do, is to take a look at, so Intel has this performance counting, this PCM software package that allows you to look at a whole bunch of different performance metrics. And one of them is the UPI bandwidth, which is how much crap is going between the sockets. So at some point I need to run that while this is running and see if it's actually isolated to the individual socket or not. Obviously they're running on different machines, it's isolated, but it's on the same machine. I mean, I guess at the same time you can still run into issues even if it's in a different box, because if you're using remote memory on the other core or on the other socket, then you can still get a performance decrease as a result of that. So
yeah,
it's just a
exactly.
question of whether you have something requesting stuff from the other socket at the same time, which would give you an even bigger performance drop.
Right. So a couple of other comments is for what we found was iPerf actually used a lot of CPU on the sending side. And there's a kernel packet generator inside the Linux kernel, a module for packet generation. And that generates a lot of packets without using much CPU. So you might want to use that.
It's at some point, I'm definitely going to take a look at that. I have used it before, but I have not really done a whole lot of experimenting with it besides just using it a couple times as kind of a sanity check. So, yeah, that's definitely a good idea to take a look at that and see what we can do.
Yeah. The other thing is, like, when we were looking at the traffic at an ISP, it's like the average packet size is about 300, and it's like a pretty bipolar distribution. It's like 50 byte packets on ACK packets, and usually like 1500 bytes for like video watching and stuff. So it's just, you know, it might be good if you had a traffic profile that's sort of similar to that, with a bunch of 50 length packets and 1500 packets that would sort of simulate what's happening on the internet.
Well, are you seeing a lot more short packets versus just opening a bunch of TCP connections? Because with iPerf running, we are getting ACK packets that are moving across the links as well in the opposite direction, right? So if you're running the TX and RX at the same time, you are going to be getting a mix of those. But it's not sending one ACK per packet, so maybe we need something to include some smaller packets as well. That is a good thought, though, definitely. I also noticed that there is a pretty significant difference between iPerf 2 and iPerf 3 in terms of the CPU usage. So I've been using both, because the nice thing about iPerf 2 is that it actually uses multiple CPUs. What a concept. iPerf 3 doesn't. If you run iPerf 3-P, it opens multiple connections, but it's only one process. So it only uses one core, which is not so great. So yeah, with iPerf, you might actually be able to take a significant bite out of 100 gig. But with iPerf 3, you got to run multiple processes in parallel, and it takes more coordination to do that. So I have some scripts set up now which will run multiple iPerf 3 processes. So that's useful. But yeah, I need to try just running iPerf again. So if I run iPerf 2, not iPerf 3, on the Mellanox NICs, that'll run at 100 gig line rate. So even 1500 byte frames. But I think we're getting a lot of help from the hardware when we're doing that, right? Because I know the Mellanox devices support TSO, and I think they also do coalescing on the receive side as well. So when that gets handed back off to the OS, we're looking at that the OS sees much larger frames. So actually, I guess that's another thing I should do. This is one thing I did for the FCCM paper, is I took I basically performed the exact same benchmarks with both Corundum and with Mellanox commercial NICs, but with all of the offloading features turned off, just to see what the performance looks like. So yeah, under that setup, you definitely see a difference if you turn off the offloading, and it does slow down. And I think we were seeing pretty similar performance to Corundum. So that's definitely something that I need to do at some point. But yeah, these performance figures that I took, the kind of preliminary, kind of rough, just to get an idea of what the performance looks like, and make sure that we're going in the right direction.
Yeah. Another comment is, instead of doing just the bandwidth, it might also be worth looking at packets per second that it can send and receive. I think that makes a lot of difference.
Well, yeah, that's a good idea. What's the best technique for measuring that? What, does packet gen and send as many packets as possible, and then see what shows up on the other end?
Yeah, what we're doing is we're using packet gen and just generating 1 byte packets, or 1 byte payload actually. So
right,
payload, and I mean, we've been getting like 3 million packets per second, and then with the page pool, we got to 15 million packets per second.
Oh, Okay, that's a
So I
pretty
guess like with the
significant
segmentation and stuff, then we'll easily reach line rate without killing the CPU.
Right. Yeah. 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 I'll definitely have to get that that page pool stuff pulled in and take a look at what the performance looks like there, because if we're talking, well, that's like 5x.
Yeah.
So
Yeah.
I don't know if that holds up
packets.
with.
Yeah, in small packets. Once you start
Right.
going to larger packets, then
It probably
like,
doesn't make as much difference. But yeah. Yeah, I mean, we'll just have to see how that. I mean, so that's kind of one of the reasons that I like doing the testing with iPerf, is that it's not just testing the NIC. You are kind of getting an idea of how it works in the kernel environment. So this is where changing some of the interrupt settings, changing some of the numbers of queues can affect the iPerf performance. But it's definitely, I mean, the downside about iPerf is you're testing the whole system. So yeah, there's definitely something to be said for doing some more kind of focused tests that are more geared towards just looking at what the hardware is doing and not what the system software is doing. So yeah, packet gen is definitely easy. So one of the things about the current setup that I have that I put together for this is the idea is that you only need to directly control what's going on one end of the link, and then the other end can then just sit there and you can poke at it. So the nice thing about iPerf is that you can run the reverse test. So you can, the remote sender will send you a bunch of packets on command. With packet gen, you would need to like have your script SSH into the other server and then load the kernel module or something. It makes the test setup more complicated. So kind of my idea with this particular set of scripts is that we can potentially use it as sort of a sanity check sort of thing with Corundum. And the idea with the script that I put together is it also runs a number of other checks. It checks to make sure it can talk to the optical modules, checks to make sure the MAC address is not a randomly generated one, and a couple of other things. It runs the PTP time sync to make sure that that does what it's supposed to do. And another thing I figured out, incidentally, is that PTP doesn't work properly on the Mellanox NICs. If there's a lot of transmit traffic, the timestamps are not consistent. So I don't know what's going on there, but I was banging my head against the wall for far too long going, what the hell did I break in Corundum, before I finally realized that if I run Corundum on both ends, it works perfectly. But if I have a Mellanox NIC on the other end, then if I have a lot of transmit traffic on the Mellanox NIC, then it doesn't work. So I'm like, okay. Oh, it also works fine with like the 10G Intel NIC. It's perfectly fine. But not the Mellanox. Even the ConnectX 5s don't work properly. So I don't know what's up with that. It's a bit of a head scratcher.
Yeah, I mean, when we started testing with Mellanox and it didn't go so well, so we switched to a SolidFlare card, and we're doing our testing with that.
Interesting. So, 100 gig?
I think SolidFlare does like less offloading and stuff. So, but I'm not sure. Anyway, another tool that we've been using is the Linux performance tool, perf, right? And so I've been getting a lot of data on the kernel module and how that's behaving. And so I'm trying to look at sort of different places on how the module is behaving. And you can see sort of like how many times each function is called, how much time is being spent in the functions and stuff.
Okay. That's
useful. So that might be useful too if like you need to make the kernel module faster. The perf tool is pretty useful.
Well, the kernel module performance is definitely an important part of the whole system, right? The kernel module is slow, then you're not going to be able to get anywhere near line rate. So, I mean, for the most part, you just try to keep it as stripped down as possible. You do as little as possible, and you hope for the best. But yeah, that definitely might be something worth looking into. Is you know, a more detailed look at what's going on in the kernel module. So you say perf is one tool for that. All right. We can certainly take a look at that.
Yeah. And again, then a question is, again, that I found from perf is, you know how the kernel module is using NAPI for the receive queues, so which actually doesn't poll, but it looks like the event queue is actually sort of doing polling, but and it's not using the NAPI stuff. So I tried implementing it, but it's just like crashed. I couldn't get it to work. since
Well,
I don't
so
really
okay,
know.
so you're saying an API is not working properly on receive?
No, it's working on the receive, but when you're calling the receive, you call it from the event queue, right? So it's like the interrupts come from the events, and then the events are handled, and then it goes to poll the receive queue. So
right.
I'm not really sure how it works on the FPGA, but I'm under the impression that you don't get an event for each packet received, right?
No.
Okay, so that's why it's sort of not a big performance hog then.
Right.
You sort of
yeah. So this is one of the reasons I've been like a little bit about implementing things like interrupt coalescing, because one, I don't think interrupt coalescing is going to make that much difference. But what might make difference is it's coalescing the event generation, right? You're basically doing interrupt coalescing, but on the generation of the events. So that might make a difference, but it is a question of, where are we going to put the state for that? How is that going to be implemented? So as of right now, there isn't a real clean way of implementing something like that. Otherwise, I would have implemented it already. But I think that's going to have to be rolled into some of the, maybe improved completion handling or improved completion queue handling, because that's used for both the completion queues, which generate the events, and for the event queues that generate the interrupts. But yeah, so the way it works right now is in the queue state, there's a couple of bits that controls the generation of events and interrupts. And basically there's an ARM bit. And when you set the ARM bit, then it will generate one event or one interrupt, and then it clears that bit, right? And then in the handler, you'll go check to see what's in the queue. There might be multiple things in the queue. Once you've done that processing, then you set the ARM bit again. And then it'll generate another event or another interrupt when something happens. So that's how the polling works, right? Because packet comes in, it fires off an event. That event then fires off an interrupt, and in doing so, those ARM bits get cleared. And then when the handlers run, then they will do their polling. Then once the queue is empty, then it will set that bit again, and it'll continue. But I guess there's probably something to be said for tuning the number of, say, receive queues to more closely match, the number of CPUs that are available. Because if you're using too many queues, then I think the polling is going to be less effective, right? Because then then the queues are going to end up empty, basically. Right. And that's not necessarily, and then it'll switch back over to events, and, that's not going to help your event rate. So I guess there's a couple different directions you could take that in, depending on what you're doing. Obviously, if you match the number of RX queues to the number of cores, that you're going to get, good performance on just dealing with all those packets. But on the flip side, if you're doing, flow steering and things like that, if you're doing more complicated classification, maybe that's not going to produce the best possible result. So not sure about that. Oh, the other thing that I should mention as well is that right now, all of the kind of receive side handling stuff or I guess all of the completion queue handling stuff is doing MMIO reads kind of on the fast path, which is not so great. Right. And as part of implementing the variable length descriptor support, I'm going to add queue state to support pointer write back, so we can have the NIC actually send that data straight back to the host. So yeah, that's a little bit TBD at this point, exactly what that's going to look like and how that's going to work. But that's definitely something that I'm planning on implementing. And that'll be optional. If you want to turn it on and use it, you can. If you want to turn it off, then that's fine, and keep doing the same thing. So yeah. I've implemented part of the infrastructure for that already. I've added to the DMA engines the ability to do immediate writes. So instead of saying, hey, I want you to read this data from here on the FPGA and write it to here on the host, you can just say, I want you to write this particular 4 bytes to the host here. And then it'll do that. So yeah, so that's implemented, and I've tested that with some of the have I extensively tested that yet? Well, I've tested it in the simulation, and I think at least one of the test scripts that I have, or I guess I don't have the DMA benchmark script set up to really hammer on that. But I did test the one-shot thing and it works. So so yeah, we'll be taking advantage of that at some point.
Another comment, since we were doing a lot of development in the kernel, right? We get a lot of crashes on the Linux side. So we did a virtualization. So we used KVM virtualization, and we would run a Linux instance in KVM, and then we could pass the PCI bus over to the virtual machine, and sort of that helped us speed up the development a lot. So
oh, that's nice.
That's interesting. That might feel. But
did you have to make any modifications to anything to make that work?
No, it's just some settings in KVM and
very
KVM
cool.
configuration.
Very cool.
But one issue is that the number of interrupts goes down to, I think, 4 or something for some reason. I'm not sure if that's because it's MSI. If we do MSIX, it will be more or not. But like we couldn't really do any performance testing that way. We had to go back to doing it on the physical machine, not on a virtual machine.
Right, yeah. So this is something that we discussed a little bit the last time, is that on some computers, MSI is limited to like one channel. This was actually the case with this machine over here. For whatever, the funny thing is this is exactly the same, or not exactly, but it's a very similar configuration to the machines that we have in the CSE building. The same series of CPUs, you know, it's a dual socket machine. It's also made by Dell. You would think you would get, you know, very similar performance, right? But no, the ones at UCSD in the CSE machine room, the Dell R540 servers, they give you 32 channels MSI. This gives you 1. And we were thinking, I mean, what the folks from MLE were saying is that it might have something to do with an IOMMU. So I did some poking around in the settings here. I couldn't find anything relevant to that. So, I mean, I thought it seemed like everything was turned on. I haven't tried with turning everything off to see if that makes a difference. But anyway, I'm like, all right, I'm just going to get MSIX working, and then we'll revisit this from there. If it doesn't work with MSIX, then we got some work to do. Because it seems like MSIX doesn't have that problem. So this is something I noticed with a couple of other motherboards. Like I have this other this is a motherboard I used a while ago for doing some testing. It says it's got very nice little feet on here, so you can just set it on your desk and and do testing with it. But yeah, first time I tried running on this, it crashed because I tried to allocate 32 interrupts and only one of them got allocated, and then I tried to use more than one and then it crashed. So yeah, I had to fix the driver to work properly if it only had one interrupt. But yeah, so when I was poking around on that going, what the heck happened? I noticed that some devices had multiple interrupts active, and those were MSIX, and the ones that only had one interrupt active were all MSI. So I'm like, what's going on here? So this seems to be just a feature of some motherboards for whatever reason. I don't have any explanation as to why that's the case, but that seems to be the case. So, but it seems to be only an MSI thing. MSIX doesn't seem to have that problem. So,
okay, so maybe hopefully with MSIX, then we can pass on like the entire interrupts to the virtual machine, and
definitely we'll have to give it a shot and see what happens. So.
Yeah, okay.
Because that's one thing that I've been thinking about a little bit too, is that it would be cool to potentially provide remote access to people that want to play around with Corundum, because we have a bunch of machines at UCSD and also here, but there's also a question of, you know, access, right? If we're going to give somebody root access on one of these machines, we don't want them, you know, screwing around with the system or accessing files they shouldn't be accessing, you know, things like that. But if we can stick them in a virtual machine and just pass the device through, hey, great. But then you got the issue of, okay, how do you forward the device to the virtual machine? If you're going to be reprogramming it, can you do that from the virtual machine and reset the link and whatnot? Or how's that going to work? So anyway, it sounds like it actually does work in a virtual machine, but potentially there's some odds and ends that need to be sorted out. So, you know.
Yeah, especially on the programming side, there might be some issues. Like,
right,
for the machines we're using, we have to reboot the machine after we program it.
Oh, really?
Yeah, I mean, I tried like the methods to reset the PCI bus and like several things, but the most reliable method we got was just to reboot the machine.
Well, okay, so the machine's not crashing, it's just it doesn't necessarily re-enumerate the device properly?
Right, exactly.
Ah,
And
yeah.
how about the performance? I mean, if you use a virtual machine, does the performance of Corundum decrease? I mean,
Well,
is it?
right now I'm using the MSI edition before all these MSIX developments. So we're just getting only 4 interrupts. So that's why the performance is really low. And
It's interesting that it's 4 and not 1.
Maybe it's 1. I mean, I was in the impression it was 4, but maybe it is 1. I'm not sure.
Okay.
So,
well, we'll have to try with the MSIX and see if that changes anything. So.
Right. Yeah. So anyway, going to a virtual machine, programming the card might be an issue, but maybe there's some way around that as well. Or maybe like you could reboot the machine from inside the virtual machine with some, API and stuff, and then the machine can come up and then start the virtual machine again, and people could
right.
use
or maybe that's a problem that you solve just with some scripts at the host level.
Right. Yeah. Possibly.
Yeah.
Another question, you know how some FPGAs have memory on them, like DIMMs? You can add DIMMs to them? Yeah. You haven't used them at all, right? I didn't see anywhere in the code.
Not yet. Yeah. That's something that I have on the roadmap, is to connect those into the DMA subsystem and expose them to the application and connect them to the Express bar and, integrate them a little bit more. I haven't gone down that path yet, so.
Yeah, that would definitely be very useful from the app space to have access to the RAMs on the DIMM. So.
Right. And then also on HBM devices to have access to the HBM.
Yes, they have, I think, enough DRAM for many things. And some bitware device have a large amount of DRAM on board.
Yeah, I know the Alveo boards and whatnot in particular are pretty good about that, because they'll have like 4 DIMMs on there that are on 4 different memory channels, so you get oodles of bandwidth.
Yeah.
Although on the flip side, I think you have to customize some of the memory controller settings based on what DIMMs are installed, which is kind of annoying, but I mean, what are you going to do, I guess? So yeah. I haven't gone down that path yet because there's quite a few question marks in terms of the implementation, right? So, are you using all the DIMMs? Or do we need to change memory controller configurations depending on what DIMMs are in there, on the number of banks, number of ranks, number of whatever? So,
I think if DRAM is used, we can offload many things to FPGA, right?
Right. Yeah. I mean, the nice thing about Corundum right now, not using DRAM, means that it's going to be fully available for the application to use. But it does need to be. We do need a path to get from the application section out to the DRAM with how things are currently.
I think it should be supported in next versions of Corundum. I mean. And the first stable version
at some point we'll get it integrated, but
not now. I think.
Yeah.
Yes, because our aim is stable version, right? And
right. Yeah. Well, so the other thing with the memory is, if Corundum supports RDMA at some point, being able to access that DRAM through the DMA subsystem in Corundum could be a very powerful feature, because then you could do, RDMA transfers just straight to the card's onboard memory instead of to the host. And if you can do that transparently, without jumping through a bunch of extra hoops, that would be a really useful feature, I think. But yeah, that's going to be a while before that sort of thing works. Anyway, let's see. So any other questions or comments on anything?
Not for me.
No? All right. I think we've pretty much covered everything. Yeah, all right. And you said you opened up a pull request for the for the page pool stuff. Yeah, let me take a look here. definitely need to take a look at that because I know the MLE guys were interested in that. Anything that can improve the performance is going to be a good thing. Which repository did you open that against?
The Alex Forensic.
Oh, okay, I see. Ah, okay, gotcha. All right, I will take a look at that then.
Great.
Yeah, I guess the one thing that MLE was kind of scratching our heads over with the page pool stuff is that it seems like that API changes periodically. So if they're running on old versions of Linux, then I guess that could potentially be an issue. Needing lots of additional code to work around old versions. Although maybe the trick is we just keep the old version around. So if you can use, so if you're on a new kernel, then it uses a page pool. If you're on an old kernel, then it uses the alternate path.
Yeah,
because I don't think they're doing anything at 100 gigs.
Support in the kernel, like what version?
So the complicating factor is that they're running like CentOS, right? Which ships some ancient kernel version, but it's complicated because it's not just an ancient kernel version. They backport all sorts of crap. So you have to look at some other information to figure out, you know, which Red Hat release you're on and what, you know, what features it contains and yada, yada, yada. So that's a somewhat different problem. I'm trying to not concern myself with that too much, but I know that's a concern for the MLE guys. So unfortunately, they're not on the call right now, but I'll definitely send them your pull request and we can discuss that. And hopefully we can get that pulled in soon. It's just a question of if they have any, you know, major concerns over over pulling in that sort of over, because we're basically adding a dependency on another kernel subsystem, which, I mean, from my point of view, it's fine if you're running on latest kernels and whatnot. But if you're looking at older kernels and you're using this new subsystem, you know, that then becomes a problem. So,
right. So
but it looks like, what?
Are they using Corundum in production somehow?
Yeah, they're building a couple of products that are using it. So yeah, it's not really in production yet, but I guess the customer wants to use either RHEL or CentOS or, you know, one of the related distributions. I'm not sure exactly which one. I guess CentOS is kind of went away. I think it's what Rocky Linux is the replacement now, right? I think that's right. Yeah, that basically does the same thing and follows Red Hat, but isn't super duper expensive. So yes, I'm not sure exactly which distribution that they're using, but it's one of those, and supporting that from the driver perspective is slightly more complicated than you know, normal kernels. Although I guess even things like Ubuntu can be problematic for certain changes. They've backported a few things and not changed the kernel version number accordingly. There's some other version information you got to look at, like Ubuntu patch number or something. So fortunately, we haven't run into those subsystems yet, but if they make a change like that to the networking stuff, then we may need to do some work. I guess that's the downside about having an out of tree driver, but you know, that's just the way things work, I suppose.
So what distribution do you use and test on?
So on all of my development machines, I'm running Arch, which is somewhat nice because they are using like the absolute latest kernel. So I might need to add some if-defs for it to work there, but then once that kernel hits Ubuntu, then it already works. So, and then I also have Ubuntu installed on my dev machines here, and then all of the machines in the CSE building run some flavor of Ubuntu. So, yeah, for production for me is Ubuntu basically. So Ubuntu LTS, one of them. Can't remember if they're running 1804 right now, if we bumped them up to 2004. Not sure. But yeah, Ubuntu LTS.
And I imagine we just tested on x86, or have you tried testing on some other architectures as well?
We only have x86 servers, so
Okay.
so
I thought so.
I have a couple of AMD machines over here, the dev machines that I have, but I don't have anything ARM or anything else. So I'm not even sure if you can get, you know, large server CPUs that are ARM, you know, on the open market. I know AMD or not AMD,
like Amazon.
Amazon has their Graviton things.
Right.
Yeah.
Right.
And I know Apple has their M1, but Apple doesn't really make servers anymore. They used to, but not anymore.
It works on AMD. Like, well, I'm doing all my development on AMD, so there aren't any issues there with AMD.
Right.
So.
Yeah, no, I've definitely done some testing on these AMD EPYC machines over here. I just have not been very enthused with the performance, even with just Mellanox NICs. I've never been able to get 100 gig out of these guys. I don't know why. Just through the normal kernel networking stack. So I don't know. Anyway, I've been putting together a couple of new Intel-based machines here. Well, new because I've getting used parts. Otherwise, I couldn't afford it. But yeah, these can hit 100 gig line rate all day long. So with the Mellanox NICs anyway. So that means hopefully we can do the same with Corundum. Anyway, yeah, it would be cool to try it on other machines, but I don't know if there is a particular machine that's available that's worth looking at. I guess there's also the Power series devices, right? I think that's definitely one that I've heard about.
Yeah, the IBM
maybe from the standpoint of everything being open source at the firmware level or at the bootloader level or something. Yeah, there's a lot of people like buying these super expensive workstations just because they were fully open source. Just like, okay, the Talos 2 or something might have been, I don't know. Yeah, it might be worth trying that out at some point. I think at some point I did an overhaul of the driver. There's some tools you can use. I think Sparse that goes through and does some type checking and whatnot, and that flagged a bunch of issues related to endianness when you're accessing stuff from the driver. So I think I have all of that sorted out. But if we try to run this on a big endian machine, I'm assuming things are probably going to break somewhere. So that's probably the biggest concern about running on another architecture. For the most part, I think, you know, PCI is PCI. It's all just memory maps, so there shouldn't really be any major issues. It's just, you know, something like the endianness is different, then you could have a problem. Other than that, I don't know if there's any other major issue you might run into running on another system.
Okay, cool.
But definitely something interesting to think about. All right. Any other questions, comments, concerns, anything? Or no, Adam John doesn't have anything. I see Alex Padilla has joined us, but he's on mute, so I guess he's not in a in a situation that's conducive to going on mute. All right. Well, if you don't have any other questions or comments or concerns or anything, then I guess it's we'll declare this a successful meeting, considering we're 10 minutes over the hour. So okay, not bad. Thanks to everyone for joining in today.
Thank you.
Great, thank you.
Have a nice 2 weeks.
All right.
Have a
Sounds
good day, Alex, and have a good night, Giray.
Okay.
Are you in
right.
Turkey, Giray? Are you in Turkey?
Yes, I'm in Istanbul.
Okay. Then have a good night.
Okay. See you. Bye-bye.
Okay.
All right. Sounds good. Talk to you.